Okay, we've got a confidence interval question here. The title of the question gives away what the distribution we're using is, but in a real life situation you might have to spot the distribution. So Poisson is talking about an average rate of phone calls. That's already a hint. And we've got a 38-hour working week, and this is how many calls we get. So I'm counting the number of calls in a 38-hour working week. So this is events in a fixed time, okay, with a constant average rate. Oh yes, she believes that that's constant. Okay, so a Poisson model is appropriate. So we are assuming, or we can proceed on the basis that we've got a Poisson random variable, and what we want to find is a confidence interval for the mean, which we don't know. Okay, now confidence intervals for a Poisson we always do using the same formula you had in S1, but this applies to a normal distribution. So I've got to approximate my Poisson with a normal, and we know that a Poisson with mean lambda approximates to a normal, and the mu for that normal is going to be lambda, and the variance is going to be sigma squared, which is also lambda, but that means that the sigma is going to be the square root of lambda. Okay. So I need to get, for my recipe, I need to set up my x bar plus or minus my z times my sigma over root n. Okay, right, now the n and the x bar, this is potentially confusing. Nearly always we've just got one observation from one 38-hour working week. I'm not saying the exam board couldn't say there are several different weeks and we've got the total from each week, but they've never actually done that. So normally we've got a sample of size 1. So n is 1. We've only looked at one 38-hour week, and the mean number of calls we've observed is just 127. Okay, if I had several different weeks, then I would have to actually do some work to find the mean of them. Okay, so this x bar is what I'm using as my estimate for the average number of calls in a week. The lambda, the population mean number of calls, I'm going to be estimating as x bar. So that's going to be at the center of my confidence interval. Okay, now I need a sigma. Now sigma is the standard deviation of that number of calls. It's the standard deviation that goes over here, and sigma squared is lambda. Now I don't know what lambda is, but I'm estimating it, okay, by this 127. Okay, my best guess for what lambda is 127. So although I don't know what sigma is, I can say, okay, I can use the square root of the observed value. So the lambda probably isn't too far away from 127, so I can use the square root of 127 as an approximation to sigma. Okay, and then finally I need the z value. Now this, if you remember your S1, this is just finding symmetrical z values on either side of the middle. The middle is at 0, of course, but I want a 99% confidence interval. So I need 99% here, so that means I've got probabilities of 0.005 on each end, and I'm going to use the left hand end because my calculator likes the left, and I'm going to go into normal inverse mode, and if I put 0.005 on the probability on the area, then it will give me a value of minus 2.576. So z equals plus or minus 2.576. Okay, and I've got a plus or minus in my formula anyway, because I need to go on either side of the middle. So now I've got all my values set up. So my x bar is 127. Okay, plus or minus z, which is what, 2.576 times sigma, which is root 127 over n, over root n, which is root 1. Okay, so I'll do that on my calculator. I probably won't bother typing in the division by the square root of 1, because I know the square root of 1 is 1. So I'm just going to do 127. Okay, for the lower limit I'm going to do minus, okay, 2.576 times the square root of 127. Not going to bother to divide it by 1. And so my lower limit, confidence limit, is 97.96. Okay, in fact 97, isn't it? It's not wrong to give quite a bit of accuracy here, though I think this is going to be quite a wide confidence interval, because 127 is in the middle. So I'm going to get a plus here, whoops, plus here. So it's all the way up to 156.03. So that is an interval in which I'm 99% sure that the true mean lies. It's quite wide because I've only got to one observation of this. So that's a perfectly good confidence interval. And now in part B, so that was part A, part B, I've got to now work out the calls per hour. Now I could go all the way back and start again with a different Poisson adjusting the mean. But because I know what I think the mean lies in for 38 hours, these two numbers of calls here, I know the number of calls is a whole number, okay? But we can use decimals on these confidence intervals. I mean, technically, we should do continuity corrections because we've used a normal approximation to a Poisson, but the syllabus lets us off. But it is appropriate to leave these values as decimals. You don't feel you have to round them off to integers. Okay, so we can divide these values by 38 because these refer to a 38-hour week, and in part B we want calls per hour. So all I need to do is divide my answers by 38. So I've got the previous one here, 38. Divide that one, answer divided by 38 gives me, so the upper limit is 4.11, and if I go back, so my calculator has remembered that calculation. There we go. That divided by 38 is my lower limit, which is 2.58. So 2.58 to 4.11. Because although the number of calls is a whole number, there's nothing that says the mean number of calls has to be a whole number. So it's entirely appropriate to put integers in here. So this is part B. I can just write down the answer. It says write down. That means I don't have to show any working. Okay, and then finally, 3 reasons why your confidence intervals are approximate. Now, we have actually mentioned them all as we went along. Okay, the first one, maybe the most obvious one, is that this was Poisson, but I've been using this recipe, which is based on a Z, which is based on a normal. So I've had to use a normal approximation to a Poisson. Okay, then when I did the recipe, I had to make do with an estimate for sigma. I'd have liked to have known the population standard deviation. If I'd known that, because it's Poisson, I'd have actually been able to work out the variance and therefore the mean. But I didn't know this. I had to estimate it using the square root of 127. So sigma was estimated. We didn't know the population standard deviation. You could even say that in context. We didn't know the standard deviation of the population of numbers of calls over the 38-hour week. Okay, but I think you're going to get away with just saying sigma was estimated. And the third thing I alluded to, okay, when you do these approximations, this 127 is a whole number of calls. We can only observe whole numbers, even though the mean might not be a whole number. And so therefore, strictly speaking, there should be a continuity correction at some point. The syllabus you're doing says you don't have to do the continuity correction, but I think it's possible that they'll just check whether you know that you should have done one. So anyhow, not very likely to come up in your exam, but you just need to be aware that we have skipped a continuity correction. So our third reason why that's an approximation is because we didn't do that continuity correction. And AQA says that's okay, so we're fine, but we need to be aware that it is approximate for that reason.